Hello, family. We are on the superpowers example as promised, and I left you hanging with this stuff in class last time I saw you. But first of all, this letter A, don't worry too much about this. It just says construct an appropriate graph to compare the distributions of preferences for UK and US. And so if you're ever asked on the AP exam to show graphically anything, just as quickly as possible, I just did some simple bars. I have the UK in red and I have the US in blue. And so you can easily compare, what did I put? FL is for fly. And so how did I get these proportions? I'm showing right here because that's a flex on your AP exam, is to show how you got at least one of them. So whoever's grading your test can see exactly what you're thinking. But what is this? A little bit more than 25%. I believe that is the 54 over 99. Okay, and then the blue one for the US is a little bit less than that. That's 54 or 45 over 99. Okay, so that's how I got my proportions there. And then a nice color code and make sure that it's well labeled, etc. Okay, and then we also talked in class on Friday about why this is a test for homogeneity. That is because we have two separate random samples, one from the US, one from the UK. It says that up here in the wording of the question, 200 children from the United Kingdom, comma, 215 children from the United States. Two separate populations, and that doesn't affect the math or the conditions or anything. It's just literally the name of the two-way test. This one's homogeneity. Remember, if we just took one sample of children and then categorized them like so, if it was just one sample, that's called your test for association or independence. Strictly the name, you got it in your reading guide. Let's move on. Okay. Remember, if I go too fast, you, my friends, have the ability to pause and copy down. Okay. What do I have here? I've got my populations. I have two different populations. And in the wording of the question, it says like 9 to 17-year-olds. I'm not sure why that's the age range, but it is. And they're both in the United Kingdom and the United States. So as specific as you can within the population, that's what you need to define. And then let's talk about the ho and the ha. So we discussed this in class last time I saw you, but the ho is usually an equal sign. Do you remember that? Where is my pen? The ho usually has an equal sign. What that means is that there is no difference. In words, equal means no difference. And then copy paste for the alternate, there is a difference. What are we even trying to show here? Difference in what? Let's talk about the superpower preferences in these two countries. That's what you're writing here, the distribution of responses for their superpower preference between the two countries, okay? And then random and independent and large sample size. Let's talk about this. Again, nobody's panicking. You can pause and you can copy down, okay? This independent condition. So random is just what we've always been doing. We have two different random samples. Here's one, here's another. So I would be specific in that random condition. You can compare that to the problem that we did earlier this week, the previous one. What was that about? This one. Oh, yeah, where you lived, okay? So we just had one random sample here, and we just did the independent condition for our one random sample that we took, which is the 10% condition. What's different about this one? Just a little bit. The random condition, we have two different samples, so I'm being a little bit more specific. And for the independence condition, when you take two different samples from two populations, you got to make sure the UK kids are not impacting the way the US kids answer the question. So our observations in our groups are independent from each other. They're not impacting each other. That's because we took two different samples. We need to make sure that that's not happening, okay? And then I'm also checking the 10% condition for both. And that is very obvious. There's definitely more than 2,000 children in this age group in the United Kingdom. And there's also definitely more than this many children in the United States in that age group. Now let's talk about large sample size. Okay, so here, what I did is I set up my matrix. And remember, I have observed 54 students right here in the UK fly category. But how many did I expect to be there? Let's talk about it. How do I get this number? And in fact, how do I get all of these expected counts? I'm going to flip over to Desmos. I already have everything typed in. And remember, you're going to the plus sign and then the inference tab. And then this is a chi-squared test for independence, okay? The independence is just the blanket umbrella like category in Desmos, but we did talk about how this is actually homogeneity, but you use the same button in Desmos because it doesn't make a difference in the math or the conditions or anything. It's just definitely not a goodness of fit test because we have two categories here that we are, well, not two categories, two different variables that are being measured here. Okay, so anyways, let me expand this a little bit more. So I already typed in all my values, and then you can see here in parentheses are all my expected values. All my expected counts, that 47.71, 46.27. Okay, family, pause the video and actually type this into Desmos and make sure on the test you're not going to freeze and not know what to do. Okay, so you can type those in and then you hit create test and then you expand both lists and you check all the boxes. And remember, we have all the answers for the entire question here, but those numbers in parentheses that you're seeing on Desmos right now are exactly what I am copying down right here into my matrix, okay? And remember what we're checking for in the large sample size, not normal condition, but large sample size. We're checking to make sure they're all bigger than or equal to 5. And you need to flex. My AP students who are going to get 5s on this thing, you need to prove how one of these numbers is calculated, okay? So remember, let's go back up. I'm sorry for zooming in and out, but how did I get this number right here? If it was a multiple choice question and you needed to prove how to get one of those values, you take the row total, which is 99, times the column total, which is 200, divided by the table total, which is 415. That's in your reading guide. These are the numbers plugged in, and that is exactly where this number came from, okay? And look, I put a little note here, show how to get one of these for full credit, okay? And you'll see multiple choice questions where they ask that also, so just be aware of that. Let's go into the math. Remember that the degrees of freedom is this formula for a two-way test because we have a certain number of rows and columns in our matrix. So the number of rows is 5 minus 1, which is 4. And then the number of columns is 2 minus 1, which is 1. And when you crunch that number, you get 4 for the degrees of freedom. Why do we need to know the degrees of freedom? Well, first of all, Desmos gives it to you. But if you're using Table C or your graphing calculator, it will ask you what is the degrees of freedom. Okay, here's my formula from the formula sheet, and I'm going to start plugging in my numbers. So first, let me zoom back out. I am comparing the 54 to the 47.7 right here. Observed minus expected squared over expected. Next, I am comparing this 45 to this number, and I'm plugging that in. And then I don't want to do that for all 10 positions in this matrix because that would take a while. But I have proof that I know how the formula works. So I'm going to put the 3 dots, and then I'm going to use the last position here, the 66 and the 57. That's what goes here. And then I'm going to leave a big blank, and I'm going to go back to Desmos because Desmos is going to calculate that number for me. Okay. Remember, when you use Desmos, don't type in the totals. Desmos is very capable of doing the totals. So your matrix just has 2 columns and 5 rows in it. Let me go back to Desmos. Here we go. You can see the chi-squared statistic under this significance test menu. It's 6.292, and the p-value is 1.178. Okay. So let me maybe shove this over so that I can continue writing. You'll notice that I have my chi-squared statistic, which is right here. Thank you, Desmos. And then be careful with your notation there. Make sure that we are always shading to the right for chi-squared, and this is the p-value given to me from Desmos, okay? And then you ask yourself, my friends, is this p too low? No. So the hoe doesn't go. So where's my hoe and my ha? Up here. My hoe does not go, so I believe this. I am going to restate what I highlighted in pink, okay? I am failing to reject the hoe, and when you fail, you do not favor. Please remember that fail and favor do not go in the same sentence. Okay, we fail to reject the null. Since I'm not failing to reject it, I'm believing it, I am in favor of it. Not in favor of it, I believe it, and that says that there is no difference. I'm restating the null. Be careful with your conclusion, okay? In the proportions of responses, blah, 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 about the context of superpower preferences between US and UK. Okay? And then remember, if you're confused about, like, I thought in this chapter we had to follow up our conclusion with something. So let me go back to Desmos one more time because remember, it can show you those components. And let me expand this. Please tell me that I did not just lose everything I typed, and I did. Okay. Remember that you can click on the individual cells in your matrix. It has the observed counts that you typed in, these numbers, and it has the expected counts, these numbers. But if you actually tap individually these cells in Desmos, it opens up the components. So these were all of the numbers from the components. You can check it in your matrix in Desmos. But when you tap the first cell, it shows you this number. When you tap the second cell, it shows you this number. Okay, and look, none of them are very large, okay? Remember, when you reject, you're supposed to be able to find some components that were very large compared to the rest. This is another example, just like we did in class yesterday, where we failed. Therefore, all of these are very small, and that gives me confidence that I have made the correct conclusion, okay? I'm going to breeze through the second example really quick, which is anger and heart disease. I'm not going to spend time flipping back and forth in Desmos. That is your job, family, to make sure that you can get the numbers that I am showing here in my notes. And once again, you can pause if you need to copy things down. Do you think that angry people are more likely to have heart disease? That is an interesting connection and an interesting thought. And what we have is a random sample of a lot of people, 8474. Tell me, you guys, is this one population or two? This is one sample from one population. The population is people with normal blood pressure. Okay? People with normal blood pressure is our population, and that's why I wrote it right here. And it's just one population. This up here was two. Look at the wording of the question. We had two different samples from two different populations. That is why we did homogeneity. That's the name of it. Be prepared to answer multiple choice questions about what is the name of the test. Here we have one sample from one population. We're back to association, just like the first question in this unit, or in this section, 11.2. Anyways, population, people with normal blood pressure. That is exactly in the wording of the question where our sample came from. Okay, people with normal blood pressure. The ho and the ha, just like we did in the previous example, we assume no association. We wonder if there is an association between how angry you are and whether or not you develop coronary heart disease. Remember that the ho always has an equal sign, no difference, no association, no correlation, no relationship. That's what we're writing for the ho in words. The alternate is copy paste. There is an association. Okay, and make sure you're using words from the problem, anger, coronary heart disease, okay? Let's check random, independent, normal. Random, we have a random sample. It's only one sample of 8474. Independence, we took one sample and we are making sure that the 10% condition is met. I think it's reasonable to believe that there's more than 84,000 people that have normal blood pressure, right? That makes sense. Large sample size. Now is where you go to Desmos, friends and family. Okay, don't just copy this down, but actually pause the video and type in this data into Desmos. Remember to hit the plus sign, then inference, then chi-squared independence test. Type in that matrix, and then hit run test or start test or whatever it says. Expand all your menus and check all your boxes, and you should see these numbers in parentheses in Desmos. And remember what we're checking them for. They're all supposed to be bigger than or equal to 5. I'm not checking for normality because chi-squared tests are right skewed, but I am checking the large sample size. They're all bigger than or equal to 5, and here's my flex. Do you understand how this number was calculated? Let me zoom out to my original problem. I observed 53 people right here. How do I figure out how many people I expected to be there? You take the row total times the column total divided by the table total. And that is exactly what I wrote out right here so that I can make sure that I get full credit, and I am proving that I know where this number came from. Full credit, 5 on the AP, 100% on the test, okay? So those are the conditions. Here's my degrees of freedom once again so that you can remember it. Number of rows minus 1. We only have 2 rows for this problem. Number of columns minus 1. We only have 3 of those. When we multiply those together, I get 2. Formula from the formula sheet. And here we go, comparing the 53. Do you think 53 compared to 69.7, is that considered like a big difference? Or what if we do all of the positions? What about 110 versus 106? That's what I'm doing here. And I'm doing the 3 dots. And then the last one is comparing 606 to 618. Are those considered big differences? It's really hard to tell when you have especially a massive matrix full of 8,400 people. Thankfully, we have stats to help us figure this out, okay? Did you get the chi-squared statistic in Desmos at 16.077? And then after you have that, does your p-value look really, really small? You can get this exact value in the calculator, or you know that it's maybe approximately 0 or very, very small. Okay, here is a different conclusion because in this case we are rejecting because the p is too low. Thank you, Snoop. That means the hose got to go. So I am rejecting this and I am believing this. And that means I'm going to restate this in my conclusion, the alternate. I'm going to say words like there is an association, okay? When you reject the null, you are in favor of the alternate and you're restating the alternate. Let's be really careful with our conclusions, okay? When you reject the null, you are in favor of the alternate, and then you restate the alternate, which says there is an association. Okay, remember, when you reject, you absolutely need to follow up your conclusion with the categories that are most likely to differ. So go back to Desmos. Where did these numbers come from? Actually find those blue bars. It tells you, like, it kind of alerts you to like, hey, right here, this is a very big difference compared to what we were expected. If you click on that cell in Desmos, you should be able to see the components for those two. Those are the two biggest components, the biggest differences. They have those blue bars right next to the numbers in the cells, and that is what we're looking for. So what it tells us is the categories most likely to differ. The biggest differences that we observed were the high anger and yes, I developed coronary heart disease. That was much higher than we thought. And the low anger and the likelihood of developing coronary heart disease. Where are those actually in my differences? Low and yes, 53 versus 69. Okay, we expected 69 people if coronary heart disease did not make a difference. And we only got 53 there. So maybe the low anger people are actually less likely to get coronary heart disease. And then this was the other biggest difference. The high anger versus coronary heart disease, we expected only 14 people, but we got more than that right here. Okay, that makes sense. Angry people maybe do have an association between their heart disease status, okay? So please make sure that you're comfortable with Desmos. We're going to be using that for this chapter. Thank you so much for listening and for watching. Hope you guys have the best day, and I will be in class tomorrow to answer all of your questions. Love you all.